Awesome, cool. So I'm going to talk about approximate nearest neighbors. I built a library called Annoy when I was at Spotify. Yeah. Is this better? No, is this necessary? Right. Is this necessary? Yeah. All right, cool. Let's do this. 3 mics. So I'm going to cover a couple of different things. So sorry, the background is I built a thing called Annoy. I used to work at Spotify for 5 years and built this thing that lets you do approximate nearest neighbor search in high dimensional spaces. So I'm going to talk about that, but also give you a lot of background about why I think vector models are awesome and you should use them for everything, and also how Annoy works, and talk a bit about the challenges and how I built it. But so first, it's going to be a little bit more background about vector models. Before that, like some info about me. I built another thing called Luigi. It's like nothing with machine learning. It's just data plumbing tool in Python. Working at a small startup as the CTO called Better. We work with mortgages. And yeah, so as 5 years at Spotify, I managed the machine learning team. A couple of those people are here in the front, so you should talk to them if you're interested in Spotify. So that's it about me. So let's talk about nearest neighbors. So nearest neighbors, when I refer to that, I mean like points, right? So you start with a set of points in some space, and so in this case, 2-dimensional space and a bunch of points, right? Kind of a trivial example here, like typically you have in the applications that I've been working on, like millions and millions of points in high dimensional spaces. This joke is getting old now, but like it's hard to fit like a high dimensional space in a 2-dimensional projector. But so that's why it's all 2-dimensional today. So what does nearest neighbor mean? It means we're going to search some part of the space. We're going to like query for some point here. It's blue. I don't know if you can see that. And we're going to look around for the points that are closest to it. So kind of simple. Like that's the basic idea. And it sounds like kind of like almost silly, but it turns out it's actually super useful in a lot of cases. So this is 5 nearest neighbors. You can go higher and higher. Cool. Yeah. So what's the point? And what I'm arguing is that turns out vector models are awesome. And as soon as you have a vector model, you have a bunch of points in some space. And you want to use nearest neighbors you want to search for nearest neighbors in this space. So let's talk about some vector models. And I'm going to start with like a super simple example. Here's the canonical machine learning data set, MNIST. It's like 60,000 handwritten digits. They're all 28 by 28 grayscale. So why is this a vector space, right? Like you can take these pixels, this 784 pixels, and kind of smash them and just make them into a big vector, and you get this 784 dimensional space, right? 28 by 28. Okay. So now we have 60,000 points in a 784 dimensional space. So now we define a distance function, okay? And in this case, we're going to make it simple. We're just going to define it as a squared Euclidean distance, right? So the sum of the squares of the differences for each pixel, okay? Does that make sense? I think so. Cool. So now we have a distance function, and we can take 2 of these pictures, 2 of these digits, and we can compute a distance. Awesome. Let me know if you have questions, by the way. I'm more than happy to like take questions during the talk. We can talk more afterwards as well. Cool. So what you can do now is, since we defined a distance function, we can actually we can take a digit and we can rank all the other ones based on how close they are in this 784 dimensional space. And so this is exactly what I did here. On the left side, we have various randomly sampled digits. And on the right side, I'm showing the 10 most similar digits from this data set. So you kind of see visually makes sense. Like we're finding visually similar images, right? Like for a human, it might not make sense because like some of the digits are weird. Like this is 8, but we're finding a 5. And we're kind of mixing up the 6s and 0s. But it is like they're like visually the same, right? And that's the point. So we effectively built a like image search engine in this like super small space of 28 by 28 pixels, right? So that's cool. So now we can, if you wanted to do like digit classification, you can train like a k-nearest neighbor classifier in this space. You can take a new image, you can look around it, find the top 10 closest ones, and just take the majority, whatever, something like that. Cool. So the problem is, like, let's say we actually want to scale this. Let's say we want to do this for arbitrary images, or for words, or whatever. I'm going to talk about text and other things later. But let's say we actually want to do this for bigger images. The problem is, we have it's already like high number of dimensions, right? 784. And say we want to go to like 1,000 by 1,000 images, right? And there's like 3 colors too. So we get this like 3 million dimensional space. So plus, like, similarity in this space isn't like perfect. Like if you want to like, if you have 2 pictures of dogs and one dog is like lower left corner and the other picture the dog is the upper right corner, like they're not going to have like a high like pixel by pixel similarity, but for a human they're pretty similar. So what I'm arguing is that this is a recurring thing, is that almost always you want to start with some fairly high dimensional space. You want to do dimensionality reduction down to like a small dimensional space, and in the small dimensional space, that's where you want to do similarity search by using something like Annoy. So again, start with super high dimensional data, 3 million dimensional data in the case of 1,000 by 1,000 pixels. You reduce it down somehow by some magic function, and now you have like a small dimensional space, like 100 dimensions or 10 or whatever, and you're going to do cool stuff in this space. Cool. So here's kind of here's something I was playing around. I wanted to learn convolutional neural networks, so I wasted a lot of thousands of dollars on renting GPU instances on Amazon. I had this crazy idea. I was gonna, I don't know, I wanted, this is kind of silly. I wanted to build an app that would predict calorie content from food pictures. It didn't work out because I ran out of time and had to do other things. But I know I ended up training a machine learning model that at least it can take a picture of a food and predict what food it is. And it actually works. So to do that, I downloaded 6 million pictures of food from Yelp. I just scraped and Foursquare. And training a supervised model that takes a picture that's 156 by 156, and then runs it through this deep neural network. And on the other side, it's going to predict words in the description text. Okay? So in this case, if it's like spicy ramen, it's going to predict some, like, a 1 in the position for spicy and a 1 in the position for ramen. It's like, multi-classification problem here. Anyway, that doesn't really matter. It turns out that, the cool thing about this is, like, I have a layer here that's 128 dimensional, which turns out to be perfect, because, like, now we're training and embedding from food down to a 128 dimensional space. Okay, so for any food picture now, or for any picture actually, we've learned a function that takes a burger and outputs a vector, right? What was I going to say? Yeah, so, machine learning is always about learning functions, right? In this case, we trained a neural network that learned this function from, burger to some vector and fries to some other vector. And it turns out in this space, for various reasons, cosine distance is a little bit better. It just means we're going to normalize these things. These are vectors now. So we're going to compute the squared Euclidean norm between the normalized vectors. But it's essentially the same thing. Cool. So what does nearest neighbors look like in this space? Pretty cool. It actually works pretty well, right? So on the left side, I put in various like randomly sampled pictures from Yelp, and then I just look for like the most similar food pictures out of a database of 6 million pictures. And it's like super fast too, because I'm going to talk later about how we do this search. Using Annoy, you can do this in milliseconds. So we built effectively a image search engine for food pictures, which is kind of useless, but kind of fun. Anyway, so it's, put in fries to get fries back. The cool thing now is like you can see like, the color. You don't really see it on this projector, but the color is like quite different for all the fries. Like there's like a little bit different scale, like positions. Like these fries are much closer to the camera. I think the other one, this one is a better example of that. Like you have these like small Asian food in white bowls, like Asian tapa, I don't know. And you can see the bowls are like located in different places. There's different scale, there's different stuff in them. But we've learned somehow to project these to like very similar 128 dimensional feature vectors. And I think the coolest one is this. There's like random desserts with patterns of chocolate over it. And I don't even know if the desserts are that similar, but the chocolates, the way they like sprinkle the chocolate is kind of similar for all of them. So it's kind of cool, it kind of works. So this is an example of a dimensionality reduction, right? Like we started with these high dimensional items, in this case pictures, that are 156 by 156 by 3. And we reduce it down to like a super small vector that's like represents those pictures. Do you have a question?
Yeah, in the previous slide, you are using a form of supervised learning to run the deep neural network, right?
You're saying I'm using supervised?
Yes, in the previous.
Yeah.
So maybe you can emphasize that because it's not fully unsupervised yet. So you have this information which helps you to find the reduced dimension.
Right. So the point is he's making is this is supervised, right? And it's supervised because we have target. We're trying to predict some quantity, in this case, food categories. But when we're actually computing the distances, like there's no cheating involved, right? Like we're not using the description text when we're computing the distances. That's purely based on the pixels.
This gives you a metric to define the distance.
Right. This gives us an embedding into 128 dimensional space. You can do this in an unsupervised way too. It's just harder because then I think going from pictures to descriptive texts, it's a way to tell the machine what we're actually looking for. If you do it like purely unsupervised, the machine might just learn that like there's a huge variation in the color in this top right corner, right? But probably doesn't matter. Cool. So this was food. You can do this for text. This is actually an old field. There's word2vec now. Like people think that's really cool, but it's actually been going on for a long time. But there's been like lately a lot of new models, in particular recurrent neural networks and long short-term memory and stuff. But it has a long history. And what all these things have in common is we're starting with some corpus or something, and we're finding these low-dimensional representations of words and documents, right? So we're taking words and we're projecting them down to some space that captures semantic similarity, right? So in this reduced space, in this small dimensional space, words that are similar end up close to each other. It's kind of a silly example, like apple and banana are similar, but less similar. That's the idea, right? And this works, right? You just need a lot of training data, big corpus of text. You can do this for documents too. I spent a couple of years at Spotify doing exactly this for collaborative filtering. So for music recommendations, we find a representation in some low-dimensional space for like music, for tracks, but also for users and playlists and artists and albums and stuff. There's a lot of matrix factorization methods came out of the Netflix prize. They're all supervised. Spotify would typically be unsupervised. Turns out unsupervised is essentially equivalent to NLP, natural language processing. You're looking at a playlist as a document. You're looking at the tracks in that playlist as a series of words. And then you can run something like word2vec. Like word2vec works really well for music recommendations. So, here's them. I've talked about this topic a bunch of times, so if you're interested, you can just Google. There's a lot of slides online about this. This is just some old material that I recycle. Here's another example, kind of like a Sunday hack project I did a couple of weeks ago. I just like pinged random IP addresses and just measured how long it takes to get a result and did a geo IP lookup to long lat and then you convert that to a point on the unit sphere, and you do like k-nearest neighbors regression on that. So this is like speed of, I don't know. You can see like in New York, like where I live, like it's close. If I ping addresses in, I don't know, Thailand, it's kind of slow. It's kind of fun. So this is my point here. Is just like you can also use this for like physical, like it doesn't have to be a latent space, right? All this previous example was some sort of latent space. You can actually use this for physical space too, right? And in this case, 3-dimensional. So this is kind of fun. And this is like, like 50 lines of Python. Okay, so let's talk about how we're actually going to do nearest neighbor search. So I built a little thing that lets you do that fast. And why do you want to do that fast? Because, if you like, it's like the alternative is doing exhaustive search, right? You can always fall back to exhaustive search. You have a point set of 10 million points, and you want to find the nearest ones. Like the most dumb way to do that is you just search through all of them, compute the distance, and just rank them, right? But for a lot of, in a lot of practical applications, that is just way too slow, right? Spotify computes recommendations for, I don't know, 50 million people every day by doing a search in this high-dimensional space. You can't do exhaustive search. You should do some faster thing. So how do you do that? Actually, sorry, I'm just going to talk about this. This is exhaustive search. So where Tvec comes with a tool to do exhaustive search. You put in Chinese river on some pre-trained vectors, and you get back a bunch of Chinese rivers. Kind of cool, like in this latent factor space of words. Takes 2.5 minutes to do that. So I rewrote that to use Annoy. And Annoy, yeah, talked about this, but one cool feature about Annoy is it uses mmap, so you can like map it from disk very quickly into RAM. It relies on the page cache in Linux or in any kernel. So okay, so I rewrote this in Annoy, and like, half a second, right? So 250 times faster. Cool. Did anyone notice something though? They're different, right? Actually, the numbers are different because I'm outputting the wrong numbers, but so that doesn't really matter. But more importantly, we're not finding actually the exact same things. Go back. So it's not exact, and that's fine. In a lot of cases, we want to trade off a little bit of accuracy for performance. So this is 250 times faster, and we're losing a couple of rivers in China, right? Turns out you can actually tweak the knobs a little bit in Annoy and search a little bit longer. And now we're spending 2 seconds, and we're finding exactly the same results, right? A little bit lucky, but it works. Cool. So bar chart. So how do you do this, right? So there's 2 steps. Like, there's some sort of magic data structure involved here. So first I'm going to talk about how to build this data structure. We're going to pre-compute a data structure, and as you might know from computer science, there's only like 2 data structures really. Like you kind of can reduce everything to 2 data structures. There's trees and there's hashes, right? Hash maps. Okay, so we're going to use binary trees actually. Okay, so here's how you build an Annoy structure, the data structure that lets you do approximate nearest neighbor search. Here's how Annoy does it. There's many ways, but this is what I like to do. You start with a set of points. Again, 2-dimensional, not so many because it'd be hard to see. And we're going to split it like randomly in 2 subsets. And the way we do that, and this is just heuristically, seems to work, is that we pick 2 random points, this one and this one, and then we split it by the hyperplane that's equidistant from those points. Okay, does that make sense? So now we have the first split in this binary tree, right? Let's split it again. Okay, so now we have 4 nodes. Okay, keep splitting, and eventually we end up with something like this. We keep splitting till we have, oh my god, the projector is like, does not like this color. It should be blue. Anyway, we keep splitting till we have, k k items left in each leaf. And the point is that the binary tree is a lot more space efficient that way. Right? So here's the binary tree. So now we have a tree here. All the squares are random hyperplanes. And the leaves, these circles, are a small set of points. So I don't know if you can see, but they have numbers in them. Cool. So we actually built the binary tree of this set of points, right? And the theory is that points that are similar in this original space, if you take a random hyperplane, if 2 points are very close to each other, they're very unlikely to end up on the wrong side of that split. Like if we have 2 points and we split it, like sorry, I wish I had 3 hands. Most likely we're not gonna like split like right between those, right? So the point of this binary tree is if 2 points are close in the original space, they're gonna end up being pretty close to each other in this binary tree, right? So that's nice. So it kind of preserves distances somehow, roughly. Searching. Okay, so this is kind of simple now. You start with your query point. Okay, sorry, the colors are messed up again. You start with your query point and just like navigate down the tree. And for every of these hyperplanes, these intermediate nodes, we just go on the side that this query point ends up being on. Okay. Okay. So what's the problem here? There's a problem. Here's the problem. Oh shit. There's 2 problems now. Projector and high dimensional nearest neighbors. So the problem here is we searched for something and we ended up in this little polygon here, and as you can see, there's actually points that are like on the other side of the split that's actually really close to them, because we like just went down the binary tree. So we're gonna do something else. We're gonna extend the binary the search a little bit, so that if we're very close to any of these hyperplanes, we're actually gonna go on both sides. Okay. So let's do like this, right? Now instead of only going through down here, we're also going down here, because it turns out this split up here has a very small margin. Okay. So cool. So now we end up with these points, like bigger set of points. And how to do that? I've experimented with various heuristics. I don't know why certain things work. Benchmarked a bit, and it seems like certain things work better than other. I don't know why. So happy. Okay, cool. And it turns out you can actually generalize this really well by, instead of like having like an arbitrary like epsilon or whatever, like you can actually use a priority queue to kind of dynamically expand. Like in this tree, you kind of first you look at all the the positive margins, and then you kind of expand and start looking at slightly negative margins, and you kind of do it from there. So you put all the internal nodes in a priority queue and then pop them and put them back, etc. This works really well. The second trick we're going to do is we're not just going to construct one tree, we're going to construct many trees, and that's called a forest, right? So, and this idea is that maybe like the first tree was like, we were kind of unlucky. Maybe we had 2 points in that space, and we randomly like ended up separating them, right? So we're going to construct the second tree randomly. And the whole point of constructing trees randomly is just decorrelate them. So that means that maybe if like we're unlucky the first time for some specific point, maybe in the second tree we're slightly more fortunate. So this is what it looks like. So this is the same point set, and we construct 3 random trees. And now if we search down the binary tree, we get different results. In this last case, actually, this leaf polygon was slightly better than the other ones, because we didn't have to even go on the other side of any splits. So we're going to do that. And typically, the more trees, the better. Like, you can construct up to like hundreds or thousands of trees if you want to. And and the cool thing is with this priority queue, it really generalizes really well to multiple trees, because you can search multiple trees at the same time using the same priority queue. What it really is going to do is it's going to like find which tree is the best, which are the splits that are like the furthest away from me, and like focus on those trees. The only thing is it takes more RAM with more trees, so you can only add trees up to a certain limit. Okay. So you know, now we got all the basic pieces in place. Let's talk about how actually we do this. You know, this is the over. So first we search all these trees using a priority queue. Then we're gonna, since we have many trees, like the same item occurs in like multiple trees, in all trees. So we're gonna remove the duplicates. And now we have a set of points left, maybe like 1,000. Now we're actually gonna go and compute the real distance for them. And then we're gonna sort it and return the top 10 or whatever. So first we go out and find candidates, you know, using these binary trees. Then we take the union, and here's what we end up with. We take every of these leaves are convex polygons, but if you take the union, it actually turns out to be non-convex. So we end up with this set of candidates, compute the distances for all these candidates, and then we return the top 10. Or in this case, I think it was top 30. Okay, so pretty good. Like, it works pretty well. You know, I intentionally made this a kind of a tricky case because there is actually 1 or 2 points that we didn't catch, right? Like, there's a couple of points up here that we actually missed, and one here. But you generally get the good points, right? And again, this goes back to like, this is why it's called approximate nearest neighbors. Like we are not going to guarantee that we get all of them, which actually turns out to be an NP complete problem in high dimensional spaces. But we're trading off a little bit of accuracy in return for like, you know, 100 or 1000x performance improvements, right? Let's talk about something slightly related to that, which is the curse of dimensionality, right? There's this theory that predicts that in high dimensional spaces we get just like weird phenomena where like the notion of like a neighborhood kind of disappears. And here's like artificial data. I just pulled data from like a k-dimensional normal distribution. So what happens is, like, if you pick a random point in this distribution and look at like how far is my nearest neighbor and my furthest neighbor, it turns out in like 2 dimensions, it's very different, right? But if you go to 1,000 dimensions, it's very similar. So why is this counterintuitive? It's like, you know, think of like a world map, right? Like in 2 dimensions, you know, the distance from New York to, you know, Washington is very small, but the distance from New York to Beijing is very huge. Let's say that the Earth was 1,000 dimensions, then the distance to every city would be almost the same. It's like really bizarre. So that's what happened in 1,000 dimensions, if you like use like a normal distribution. And here's like a world map, right? And this is a Voronoi tessellation. If we start with a random point set, we can do Voronoi tessellation. They look kind of cool. And if you look at the neighborhood graph, which is called a Delaunay triangulation, I think. If you think of this as a map, like, you know, most countries only border like 1 or 2 other countries, or 3 or 5 or whatever. In 1,000 dimensional in the 1,000 dimensional world map, like every country would have a border shared with every other country, roughly. So this is sort of like weird things that happen in high dimensional spaces. Okay, so this doesn't mean we're screwed. So maybe, yeah, it definitely means that things are harder. And you can actually, there is some proof that you cannot do exact nearest neighbor search in less than linear time in high dimensional spaces. There's also this theory that says this quantity goes to 0, right? But so let's see what happens when we actually look at real data. You know, this is synthetic data from a normal distribution, and then I'll actually look at some real data. You know, various word vectors, various. You know, this is the food vectors. We got the digit here. So at least using this quantity, which is kind of arguable, you can see that the data behaves as if it's actually low dimensional. So we have a 1,000-dimensional set of points, but it's effectively behaving, if you look at this free-base vector, which is 1,000 dimensions, it's behaving as if it's 15 dimensions. So that's kind of cool. And the way I think about it is like, yeah, like if you have a map of all the cities in the world, they are in 3-dimensional space, but for practical purposes, like they kind of behave as if they're like 2-dimensional, right? Because everything is on a surface. So I think that's what happens in these high-dimensional spaces. It turns out some of the dimensions matter very little, just that like altitude matters very little on the surface of the Earth. Like what really matters is like 1 or 2 dimensions. So this is kind of cool, and I think this is, for me, this is proof why Annoy actually works, although it shouldn't work, or any of these approximate nearest neighbor methods, is that if you actually have some awareness of the distribution, then you can kind of, you can still search for nearest neighbors in this space. Cool. Another thing that I kind of like about Annoy is that it's not just about like improving accuracy or improving performance. An improvement in accuracy, actually, you can kind of reinterpret that as a performance and as an improvement in performance. So you have this like weird case which I think is fun, where I can choose to like build my machine learning algorithms better, and that could improve accuracy. But I can also like think about how the page cache works or how the CPU cache works. And that means I can search more nodes, and that means I can actually get more accuracy. So it's kind of like, you know, like a chess AI, right? Like that's why people are so obsessed with like bitmaps and shit when they try to write fast chess AIs. It's more than just having smart algorithms. It's also like being like fast, right? So I've spent a little bit of time optimizing Annoy. I did a benchmark against a couple of other libraries. So these were the top 4. So you can check it out. So Annoy is actually not the fastest one. It's like half as fast sometimes. But when you get to this, you know, at some point over here, like high accuracy, which I think is like practical settings actually the most important case. When you want like 95% accuracy, turns out Annoy is actually the best one in this data set, for this data set at least. But there's a couple of other ones that work a little bit different. Cool. There's 2 trade-offs with Annoy. One is like adding more trees, and the other one is like you can just sort of in runtime search for more nodes. But yeah, you can explore that. And I'm sort of wrapping up now, but just wanted to mention a couple of things. I've tried a lot of things to improve this. There's a lot of things that worked. There's more things that didn't work, but a couple of things that work is, you know, thinking about how to split planes and CPU caches and things like that. There's a lot of things that didn't work. I spent like a lot of time trying to do like 8-bit floating point arithmetic. It doesn't really work for some reason. I don't know why. Yeah. A lot more things I want to do in the future. I wish I had more time, but if you have time to actually help me, I'd love to chat afterwards. I realized the other day that like it'd be really cool to support edit distance, because it turns out Annoy actually doesn't really rely on like having like a sort of Euclidean space. You can actually have sort of like arbitrary distance functions, so that would be kind of cool. There's a lot of stuff I want to do. But yeah, that's it. Go check out Annoy. I put the benchmarks up. This whole presentation, most of it is actually open sourced, all the scripts that generate the slides. If you care, go check out my blog, follow me on Twitter. And that's it. And we're hiring, by the way, just in case. So if you're interested, if you're looking for a job, you should definitely talk. Cool. Thanks a lot. Do you have any questions? Yeah. What's that? The priority queue heuristics. So the way it works is right now is, let me go back to like how binary tree looks like. Okay, here. Actually, let's go back all the way to this one. Okay. So the heuristics. What I mean with that is, you know, every point here when you search, you're going to compute a margin, and but you know so you want some heuristic that's based on like the margin at every of these steps. And I tried the sum. It didn't work as well as just using the minimum margin of this. I don't know why. Does that make any sense? It's magic to me. Like, I'm sure there's some like mathematical reason why. But you know, so you want some sort of heuristic. It's kind of like A-star search, I guess. You have some like heuristic to like prioritize how you search in this space. For some reason, it just turns out that like the minimum violation of, or sorry, the max violation of how far you go into the other side of any split is the best heuristic. I don't know why. Cool. Any other questions?
I'm surprised you didn't use the normal term for this implementation, which would be locality sensitive hashing.
Yeah.
This is a typical implementation of Charakar's.
Yeah, so the question is about locality sensitive hashing. I've tried that. I've never got it to work well.
Well, that's this.
Well, locality sensitive hashing, it doesn't construct a tree, right? It only constructs a set of hashes directly from a point set.
In the case of Charakar, it's just literally which side of a series of randomized hyperplanes.
Right. So
sits within.
right.
So that just becomes, in this case, a hash function drawn from a series of binary values.
Right. Exactly.
Doing a lookup, then you're doing a lookup using a binary, a binary.
Right. So the point of locality sensitive hashing is instead of building a tree, you just have a bunch of root nodes, and you just compute what side of the root nodes your point falls on. Is that correct, right?
Perfect.
And then you get a binary representation that represents any point in this space as a binary string, and then you can use that to hash. My experiments was I never got it to work well. I suspect it has something to do with the fact that it's not really aware of the distribution of points. It's just using random splits. So, if you have a 1,000-dimensional distribution, and it turns out that the points are mostly spread out along one axis, a lot of those random splits are just going to be like not contribute any information at all. And that's my experience. I don't know. A lot of people use locality sensitive hashing. I haven't really seen it work well for the stuff that I've been doing. Cool. More questions?
Just to follow up slightly on that, the point that you were making about the impact of the data sets that you're seeing, isn't that just classic sparsity? So in other words, over sufficiently high dimensional spaces, that you're still getting a large clumping of the data into, that the actual distances are between these data points in high dimensional space are actually relatively clumped. So you've got either you've got sparsity, so that you've got much higher dimensionality than you have your data points being represented evenly across that dimensional space.
I'm not sure I understand the question. Like typically you have like more in the things that I've been looking at, you have far more points than dimensions. But I still think it's not a matter of like lack of data, if that's what you meant.
No, I mean just literally that you're not seeing an even distribution across your entire dimensional space.
Right. I think the reason why the conditions where locality sensitive hashing works is if you have like a normal distribution. But it turns out in reality, in most cases, you have some high dimensional set of points, and there is some underlying distribution that generated those points. We just don't know that distribution. And in that case, if that distribution has like high regularities, then I think LSH fails to take advantage of those. Whereas if you construct a binary tree, you're sort of dynamically discovering that structure. Cool. More questions? Yep.
How does the algorithm deal with outliers?
How does the algorithm
Deal with
outliers?
outliers?
Outliers, I think, actually work really well. If you think about how a Voronoi diagram looks like I think, in the edges of these it's pretty far in between these, these fields get bigger and bigger. So if you're searching for some point out here, the sparsity is much higher, or the density is much lower. I don't know if that makes any sense. Actually, the truth is I don't know. I'm just making something up right now. But I think it's actually, it gets easier with outliers. I think it gets harder like in here, in this like cluster here. Yeah?
How many trees you end up using? Like
How many trees do I end up using? Typically like 100 maybe, or like 10, or I don't know, 10 up to 100. Whatever, like how many you can fit in RAM efficiently. Every tree takes some amount of space. So it's like how much RAM you have on your computer. You don't want to like run over that, because then you're going to start swapping and then you're screwed. But up to that, more trees generally always help.
So you said like you tried like to play with the precision of one of the like point vector presentations, or?
Yeah, so I played around with how do you represent these vectors, like a series of 32-bit floats. I tried like reduce that precision to like 8 bits. But yeah, it doesn't really work. I think it has something to do with the fact that the bottleneck is actually memory latency. So it doesn't really matter that you're fetching less data. What matters is like you still have like the exact same amount of random access cache misses, or I don't know. I'm speculation, not right now, but I think so. Cool. More questions?
How often do you end up having to update the tree as compared to make queries against it? Is the tree fairly static?
The question is, how often do I update the tree? So Annoy does not support updates. The data structure is like fixed. So you pre-compute it, and it is what it is. So typically the way we did it at Spotify was every few days we would run like a new matrix factorization algorithm on the listening data, and we get vectors, and then we compute an Annoy index. And that was the Annoy index for next few days. Yeah, at some point I really want to support like updates, but it's just messier. Cool. Yep.
I was just curious, have you ever like visualized like T-SNE, like sort of projected the points onto a two-dimensional space and then looked at how categorization happens?
Yeah. So the question is about T-SNE. T-SNE is a cool method that is mostly, it's good for visualization. It has this cool ability that it takes some high dimensional point set and it kind of warps it down to like 2 dimensions in a way that similar items are still close to each other. I don't know, I have multiple theories that are like in conflict with each other. I think maybe that should work. Like maybe you can take like a 1,000-dimensional data set and do T-SNE down to like 10 dimension before you build an Annoy index. Maybe that would work. On the other hand, if the intrinsic dimensionality is already pretty small, then you might not gain that much from doing T-SNE. And the other thing is that T-SNE, there's certain, like as you're warping this space, you suddenly lose certain things. Like, you might actually have, like Spotify did this thing where like user vectors were computed separately from the Annoy index. So now if you like warped the set of the music space, you still have these like user vectors, and you have like no idea how to warp them, because T-SNE doesn't learn a function; it just learns a mapping. So that's a problem. So you're throwing away information, I think. Does that make any sense?
Sure. So I guess what I was imagining is using Annoy and then with the same data using T-SNE to visualize it, and then sort of looking at.
Oh, the question is, can you use T-SNE for Annoy for T-SNE?
No.
Because you can do that. That would be a very easy implementation of T-SNE. Just load everything into Annoy.
I was thinking of doing. Maybe I'll come.
All right, cool. Yeah, I'm a little confused what you mean. Yeah.
What did you say your distance metrics were?
Well, there's only 2 distance metrics that are supported by Annoy right now. The one is Euclidean, so kind of basic. The other one is cosine, or technically it's like you normalize the vectors and then do Euclidean distance. So that, of course, that's equivalent to like cosine similarity. But there's nothing that like prevents us from doing like Manhattan distance, and I never know how to pronounce this, Mahalabuna distance, or like even like edit distance. Right? Yep. What about computing and embedding? Yeah, I mean, that's what I've been kind of arguing. Is like you want to do some sort of dimensionality reduction, right? Is that what you mean? Like, because like that's exactly what we learned using this neural network, right? We learn an embedding in 128-dimensional space, where we start from like a big dimensional space, and maybe you can do even more. Like maybe as a part of Annoy, it can like on top of that iteratively learn another embedding. I don't know. I think that'd be very cool to explore. I don't know. A binary? Yeah, I mean, like, last 20 years of machine learning, like, the, like, recipe for success has, like, always been that, like, don't, like, come up with, like, various heuristics. Actually define a loss function and, like, optimize that loss function. So I think in the case of Annoy, like, I'm repeating the same mistake. I'm just defining a bunch of heuristics for how to split trees. I think what you really would want to do, and I think this would like kick ass, is you would learn how to split those trees in such a way that you minimize the divergence between the distance in the original space and some sort of new form of distance in these forests of binary trees. But yeah, that you could probably figure out how to do that. I wish I had more time and like I don't know, more computers. More question? 2 more minutes? 2 more questions? 2 more questions. 2 more. Who wants to do the first one? It has to be very, very good question. No, I'm just kidding. Come on.
Skip the first one and just do the second.
All right, let's do the second question. All right, one over here.
So the size data set that you're looking for, it's an optimizing via Annoy.
Yeah.
To either optimize, presumably for time. Is this implicitly available also to make concurrent? That is to say, is it a data parallel application by your design, or are you experimentally just looking at algorithms at this stage?
I'm not sure I understand the question. There are like pre-computation trade-offs, which is like you can build more trees, and then there's a runtime trade-off, which is you can choose how much you want to explore in the search space. Is that what you meant?
Well, really, I was thinking in terms of, for this particular implementation, how grossly parallelizable is it?
How parallelizable is this? I haven't focused too much on parallelizing it. Like, building the index is very parallelizable, because we're just building a bunch of binary trees, and they have nothing to do with each other. So you can just build all of them in parallel. I haven't done that because, I don't know, for me, it hasn't been a problem. Searching is slightly less parallelizable, but you can add a mutex on the priority queue and just have a bunch of workers. In reality, that hasn't been an issue for me, because what you can do is you can just use, like in all my application, I can just use multi-processing instead, because Annoy uses mmap, right? So you can share a static data set between processes, so you don't even have to deal with locks. So instead of parallelizing each individual search, you just do many searches at the same time. Because typically the applications that I work with at Spotify was like batch processing anyway, so it didn't really matter. Cool, what else? One more question, or is it 0 now? Did we skip one? Okay, I'll give you 10 seconds.
What are you doing now?
What am I doing now? So I run the engineering team of a small startup. We work with mortgages, building a mortgage bank from scratch. Super cool. Got a couple of the team here, a couple of people from the team. Mostly hiring backend engineers. But eventually, I really want to start thinking also about machine learning and how we can build machine learning to predict home prices and forecast home prices and risk models for borrowers. And there's all these like cool machine learning problems. So that's something I want to start hiring for later this year. So if you're interested in like mortgages and homes and American dream of home ownership, you can talk afterwards. Awesome. Thanks a lot.